Hello everyone, welcome back to my channel where we have fun calculating some rather difficult integrals. And today's integral, number 2, isn't particularly difficult. It's a practical example of how to handle Leibniz rule and Feynman's technique. This integral is the one I told you about in the first video of this channel. It's an integral that can be calculated using many different methods. But you will see that all these methods loop together quite easily. In fact, there are only 3 ways of doing this. The first one is with complex analysis, the second one with rule analysis, and the third one with the trick of splitting the integral in 2 integrals, We'll only do rule analysis here, and we won't use the trick of split the integral. Because, well, I'm not very good at complex analysis and I'm afraid of talking nonsense in my explanations, and I think splitting the integral is not the most useful case to work on iteration techniques. So I will keep this integral in one piece. The easiest way to proceed is to try and get rid of the logarithms here. The first one, log x, can be pretty easily removed. Here's a hint. Look at the denominator. That 1 over x squared should give you a clue. In fact, even if the power of x were very slightly different, the integral would still converge, and probably to a fairly close value, since the function varies very little when the power is changed very slightly. This indicates that it is possible to use Leibniz rule to get rid of the log. We introduce the parameter s such that the integral depends on x to the power of s. And the integral we're looking for would be the one with s approaching -2. And now, a simple question: should we use Leibniz rule or Feynman's technique? Well, let's see. Since we have a log x in the numerator that we'd like to see disappear, we can already know which technique is the most useful. We can do a simple Leibniz rule, which means pose a generalized integral, and its derivative would give us the integral we're looking for. We can also use Feynman's method, which consists in taking this same integral but with a new parameter s. So instead of this 1 by x squared, we have, for example, here x to the s power. Then we have to differentiate this new integral, and differentiation reveals a log x factor, which should help us calculating the generalized integral. Which means, if we use a Feynman technique, we'll add up here a log x in the numerator, which means we'll be using log squared x, which is even more difficult to calculate. So the Feynman method is therefore not the right one here. On the other hand, with a Leibniz rule, we can start from an integral with the parameter s here, but without this log x. Then we have to calculate the general case and finally differentiate, which means that the Leibniz rule will help us here, much better than the Feynman technique. So we set it up with a parameterized integral I of s, which equals the integral from 0 to infinity, because we can't change the boundaries here. The integral from 0 to infinity of x to the s power log 1 plus x squared dx. And if we name this integral I, so that we have something to refer to, according to Leibniz rule, because here this integrand is continuous and the integral converges for s around -2, we know that I prime of s equals d by ds integral here from 0 to infinity of dx, which equals, according to Leibniz rule, to the interval from 0 to infinity of del by del s x to the s power log 1 plus x squared dx. And here, as log 1 plus x squared is a constant with respect to s, this equals the integral from 0 to infinity of x to the s power log x, log of the base, log 1 plus x squared dx. And here we have our integral I if s approaches -2. We can do here limits, so the limits when s approaches -2 of I prime of s, but here the integral I prime is continuous, so we can just calculate I prime of -2. This integral is already defined, not only as a limit. So we now have a generalized integral that we have to calculate that contains only one logarithm and in fact not the nicest one. However, we can certainly solve the problem in a whole host of different ways. But all these ways lead to a single outcome, the use of a special function, the beta function. The beta function is defined as an integral, so beta of, let's say, alpha little beta, here is a capital beta, is defined as the integral from 0 to 1 of x to the alpha minus 1, 1 minus x to the beta minus 1 dx. This function is symmetric for alpha and beta because we can do the substitution x goes to 1 minus x and we see that the arguments are switched up. So beta alpha beta equals beta beta alpha. This is a very important special function in analysis, and well, I haven't mentioned it on this channel yet, but we'll be seeing it regularly as it's a function that can be used to calculate all kinds of integrals, even generalized integrals. The function looks like this. Beta of alpha beta is defined as this way, but we have many substitution for x here, and one very important integral representation of the beta function is a trigonometric one, which we'll see in a few videos. The case which will help us here is this one. Beta of alpha beta equals the integral from 0 to infinity of x to the alpha minus 1 power by 1 plus x to the alpha plus beta power dx. Here we know that alpha and beta have to be greater than 0, else the integral here won't converge. But we could still define the beta function in another way that permits to have some negative arguments, but there is no a single integral representation that would converge with a negative argument. This function is very helpful for integrals because it can be linked to another special function, much easier to handle because we know that, and it's a very important theorem, beta of alpha beta equals, and this is in terms of gamma function, gamma alpha, gamma beta divided by gamma alpha plus beta. which I will prove this here in a next video. Not now, we don't have the time. This integral here should not link us to the beta to our integral I, because here we have some x squared. But if you think about it, in fact, even if we had x to a certain power, we could still link it to the beta function by a substitution. Like if here we have 1 plus x squared, this won't be a problem at all. So no problem with this 1 plus x squared. And this function, I assure you, is the one that will enable us to solve our integral I, or in fact, our integral I of s. If I were in a hurry, we could do a silly IBP, because differentiating the log 1 plus x squared and taking the entire derivative of x to the s power would automatically link us to the beta function. However, to get us working on Feynman's technique, which we haven't used before apart from the canonical example in the previous video, we'll see it here. With a logarithm, Feynman's technique is very easy to implement. We need to introduce a second parameter into the log, and this time arbitrarily named a. So let's say I of s a equals the integral from 0 to infinity of x to the s power log of something, dx. And we have something here that looks like 1 plus x squared, but we have to add a, in fact, that allows us to differentiate with respect to a, in here or here. We need to place the parameter in such a way that as to be able to differentiate with respect to a, and don't forget about it, calculate the generalized integral. And we have three possibilities here. First, we could place the a in this place, in the place of the 1, and so we have a plus x squared, and we're looking for the case a equals 1. We can also do 1 plus a times x squared, and then we're also looking for the case a equals 1, and finally 1 plus x to the power of a. The case a plus x squared could work, but in fact, because s has to approach -2, if you say that a is different of 1, the integral won't converge at all. So this could have worked if we had a bigger parameter s, like s equals 0, but then the boundaries wouldn't fit right. So this a plus x squared won't work here. And in fact, the 1 plus x to the a power won't work as well, because, well, we don't have an easy case to calculate, if you remember right. But, well, I'll set more explanations in the comment sections. So take a look if you're interested in these techniques, but only one way. But we have only one way to work, is 1 plus a x squared, because even if a is different of 1, this integral still converges for s approaching -2. So we need to keep the second idea. And let's say that I of sa equals this integral, the integral from 0 to infinity of x to the s power log 1 plus a x squared. And we're trying to evaluate our particular case, I of s1, by Feynman's technique, which means differentiation, then taking an entire derivative. So we have to differentiate with respect to a and applying Leibniz rule. So let's say that I prime of sa is del by del a I of sa. because for now we won't be using I prime of SA, we're differentiating with respect to S, so we only have to differentiate with respect to A. So we just pose I prime. So I prime of SA equals the integral from 0 to infinity of del by del A x to the S power log 1 plus A x squared dx. And here x to the S power is a constant with respect to A, so we have to differentiate this log 1 plus A x squared, and here is x squared is a constant factor for the A, so this goes to, after differentiation, goes to x squared by 1 plus A x squared. So our generalized integral is I prime of SA equals the integral from 0 to infinity of x to the S plus 2 power divided by 1 plus A x squared dx. And we want to link this to this function. And we see that the only problem here is this egg x squared that should be only x. So how can we solve that problem? Just letting a new variable, let's say u being equal to a x squared. And this way here we have 1 plus u, and here we have, well, square root of u minus u by a. But it's not a problem, because here this is a power, and a is a constant, so we can take it out of the integral. So our substitution leads us to du equals 2ax dx, and dx, well, x dx equals du by 2a. The limits of integration remain unchanged because we can just assume that a is greater than, greater than 0, but we can let a approach 0 plus here. This will be important later, not for now, but a is never negative. So I prime of SA equals 1 by 2a times the integral from 0 to infinity of, here we have x dx, so we have to take 1x outside of this x to the s plus 2 power, so we have x to the s plus 1 power times x dx here. So x to the s plus 1 power becomes u by a under square root. Here x equals square root u by a, so we have u by a to the s plus 1 by 2 power. All this divided by 1 plus u, and we have the u right here, because 1 by 2a is already outside of the integral. Which means I prime of SA equals, we take this a to the s plus 1 by 2 power outside of the integral. I prime of SA equals 1 by 2 a to the s plus 3 by 2. Be careful with this 1 power and s plus 1 by 2 power. Times the integral from 0 to infinity of u to the s plus 1 by 2 power by 1 plus u du, and this can be linked to our beta function. Here we know the arguments. We know that this is beta of alpha beta, where here this is alpha minus 1, and this here, 1 plus u, is to something power, which is alpha plus beta. So now we can identify here alpha equals s plus 3 by 2, and beta equals 1 minus alpha, because the sum equals 1, which is negative s plus 1 by 2. Thus, I prime of SA equals 1 by 2 a to the power s plus 3 by 2, beta of s plus 3 by 2, negative s plus 1 by 2. And here you can check that this function is still defined for s approaching negative 2, because here we have negative 2 plus 3, so we have 1/2 here, and here we also, I forgot this negative sign, sorry, we have negative 1/2, but with an extra negative sign, so we have, when s approaches negative 2, this goes to 1/2, and this also goes to 1/2. So the beta function is defined for positive arguments, which is a great idea when dealing with integrals, because if the beta function is defined with negative arguments, then the integral representation doesn't converge. So we have this beta stuff here that is defining our I prime of SA. And we now have to use this relation, knowing that here alpha plus beta equals 1. So this equals 1 by 2a to the plus 3 by 2 power gamma s plus 3 by 2 times gamma negative s plus 1 by 2 divided by gamma 1. And we know that gamma n equals n minus 1 factorial for n starting at 1. So here gamma 1 is just 0 factorial, which is 1. So I prime of SA equals 1 by 2a to the s plus 3 power by 2, a to the s plus 3 by 2 power, sorry, times gamma s plus 3 by 2, gamma negative s plus 1 by 2. And now we have to use a crucial theorem around the gamma function, which is the Euler reflection formula, which is a very important formula that I will prove in a next video. Gamma of 1 minus theta times gamma theta equals pi cosecant pi theta, where cosecant is just 1 by sine. We now can write our integral I prime of SA in terms of cosecant. I prime of SA equals 1 by 2a to the s plus 3 by 2 power times pi times cosecant of here s plus 3 by 2. Times pi. So now is the time where we get rid of our parameter a, and to do this we need to take an antiderivative of our I prime function with respect to a, I mean, because here I prime is the I function differentiated with respect to a, so now we have to integrate back to get I of SA. I of SA equals the entire derivative of del by del A I of SA dA, which equals pi by 2 cosecant of pi s plus 3 by 2 times the integral, well, the entire derivative of a to the power of negative s plus 3 by 2 dA. And remember that s is a constant for this integral, which is only for a. So we can consider that s is a constant which is a round of negative 2. And then we have to integrate into a to the power of negative s plus 1 by 2, all divided by negative s plus 1 by 2. Plus, be careful, plus capital C. And here we have to add a constant plus c, but be very careful. This is a constant for this integral, which means it's a constant with respect to a, which means it may depend on s here. So we must be very careful in our understanding of the term constant. This constant can be easily evaluated with a special case for our integral that makes it easily doable. The simplest case we know of here, this integral, is the case a equals 0, or as we know, a is greater than 0, which means a approaches 0 plus. But, well, the integrand here is continuous, so when a approaches 0 plus, this goes to 0 anyway, and the integral goes to 0. So I of s0 equals the integral from 0 to infinity of x to the s power log 1 plus 0 x squared dx. And this is just log 1, which is 0, so we're integrating 0 on the segment 0 infinity, which is 0. We can link this to our capital C constants. Here, if we let a approaching 0, what do we have? We have here a to the negative s plus 1 by 2. So this a shall be replaced with 0. And if you think that's, oh, this is 0 to a negative power, so this goes to infinity, don't worry, because we can say that s approaches only negative 2, which means that this here approaches negative 1 by 2, so we have a to the 1/2 power. So when a is replaced with 0, we have still 0 in here. So this equals, for a approaching 0 plus, this equals 0 plus c. And as this equals 0 without plus c, we know that this implies capital C equals 0. And as you see, this is a constant, well, 0, which is constant with respect to a, but also with respect to s. But this is not always the case, so we need to be very careful with this when using Leibniz rule and then Feynman's technique. Our constant term may not be constant at all. It can be a function of S. So we have a general expression for I of SA, which is this expression without any plus C this time. So I of SA equals, here we have by 2 and by 2, so this and this simplifies, and we have negative pi by S plus 1 cosecant of pi S plus 3 by 2 times just here when A approaches 1. Nope, here, so we don't have A approaching anything. We have just A to the negative power S plus 1 by 2. And the interesting case is for A goes to 1, or A equals 1 in here. I of S equals I of S1, which equals negative pi by S plus 1 cosecant pi S plus 3 by 2. And we now need to differentiate our function and take the case S equals negative 2. By differentiating, we have I prime of S, and here I prime is totally okay because we have only one parameter left. I prime of S equals, so we have the product rule, pi by negative S plus 1, so S plus 1 squared cosecant pi S plus 3 by 2. Okay. Minus pi divided by S plus 1. And here we have the derivative of cosecant pi S plus 3 by 2, which is negative pi by 2 cotangent of pi S plus 3 halves cosecant pi S plus 3 halves. And well, I'm not going to simplify anything because here we know that S approaches negative 2. Which means that in here we have something approaching to negative 1. So we have negative 1 by 2 times pi, which is negative pi by 2. And cotangent is just cosine divided by sine. So we have cosine pi by 2 by sine pi by 2, which is 0 by 1. So this goes to 0. And this is defined, this is a rule. So we know that this goes to 0, this is defined, and this is defined, but anyway, because it's a sum, so here all this product goes to 0 when S approaches negative 2. So we're only left with pi by negative 1 squared times cosecant of here pi negative 1. What am I talking about? Okay, here with this was not negative pi by 2 but just pi by 2, but well, it doesn't matter because cotangent negative pi by 2 is indeed 0. And here we have cosine pi by 2. Cosine pi halves, which is here pi times 1, because 1 by sine pi by 2, which is pi. And this means that the interval from 0 to infinity of log x log 1 plus x squared divided by x squared dx equals pi. I hope you now understand the concept of Feynman's method and Leibniz rule, because we'll go faster next time. This video was far too long for the YouTube algorithm, but it was necessary to give you an example of how to apply Feynman's technique and Leibniz rule. We have gained in fluidity by doing an IBP here, but at least now everything is clear about Feynman and Leibniz. The next video on annual number 3 will be out very soon, I hope, and we'll deal with an annual that's not particularly difficult, but more so than this one. It uses concepts that are fairly common in iteration at the interval from 0 to infinity of log squared x divided by square root x 1 minus x squared dx. And I suggest you think about what we've done here to see how to set up a Leibniz tool to blow up these algorithms, which will make the interval easier to visualize. And I also suggest that once you've got the idea, you understand why it won't work at all as well as the manipulation we did today. This video will indeed be without Feynman's technique or Leibniz tool, as will the video on interval number 4, which will be released afterwards, and which will cover a very similar interval, but one that's a hair more difficult still. I don't think it's a good idea to do too much Leibniz in interval calculus, otherwise we'll miss out on all the great ways of doing intervals that are available to us. We'll see you in the next video, in which you might learn a thing or two. It will be based on the polygamma function, and Hurwitz's data function will make a brief appearance, but I will save it for interval number 4. Try interval number 3 first, and until then, study, learn, and progress.